You may have heard this from your mom or your grandmom that never store pickles in copper vessels. Why? That's because copper reacts with acid to form poisonous metal oxides. So you may ask, where is acid? Pickle has lemon in it and lemon has citric acid. So here we are talking about a reaction between a metal and an acid. Hello friends, so I am back here with this video to discuss about many such reactions of acids and bases, how they react with each other, how do they react with metals, metal carbonates, metal bicarbonates, metal oxides and so on. So let's get started. How do acids and bases react with each other? Now this is a very popular reaction and is often known as neutralization reaction. Why? That's because acid and base combines with each other to form salt and also to neutralize each other's effect. So basically the acidic nature of acid is neutralized, the basic nature of base is also neutralized to form neutral salt along with water. Okay, so let's perform this simple activity to understand how neutralization takes place. So let's suppose you have a test tube and you have put, say, approximately 2 milliliter of dilute sodium hydroxide, right? So we know that this is a base, but that is something that we know. But in order to prove it, so we can use an indicator. So the indicator that we have used here is phenolphthalein. So what we do initially, we add phenolphthalein indicator and we just add 2 drops of phenolphthalein. As we do that, we see that what happened? The color changed from colorless to pink. Okay. So why did that happen? Because that's the nature of phenolphthalein as an acid-base indicator. So it turns colorless, it turns pink in color whenever it is with base. Fine. Now, as next step, what we do is we add dilute HCl. So now we add dilute HCl and we continue adding it drop by drop. So it's not that we just add 2 drops or 1 drop. We keep adding it drop by drop. So what do we notice? So we notice that the color changes from pink to colorless after some time. So now I can ask you that why do we see this change now? Now what happens is when we add dilute hydrochloric acid, a reaction like this takes place. Sodium hydroxide combines with hydrochloric acid to form sodium chloride and H2O. So basically the basic nature is lost, the acidic nature is also lost. Right? So they neutralize to form a salt. So as a result, this is no more basic. So phenolphthalein is pink in color only when this solution which is there is a base. But right now the basic nature of the base is lost. So as a result, the phenolphthalein becomes colorless. Right? Now an interesting thing to note here is now this reaction takes place in this fashion that since we continue to add this HCl, right? So initially the effect of HCl is neutralized. Why? Because we also have NaOH, sodium hydroxide, which is a base. But after all the NaOH is over, because NaOH is limited here, we just have 2 ml of NaOH. But HCl we are, kind of adding drop by drop. So after all the NaOH is over, then we see the change in color. That is, then only we see this colorless thing. Because this colorless thing means that it is acidic in nature. That is when phenolphthalein turns colorless, right? So initially it is like neutralization. So it's like there's no change in color because it is all neutral, right? But after some time what happens is the base is all used up because we have limited stock of base. Base is like in limited quantity. So then what are we left with? We are left with acid, that is dilute HCl. And in acid, what is the color of phenolphthalein? Colorless. So that is why while performing this experiment, you will notice that this change in color doesn't happen immediately after you add dilute HCl. So initially you do not see any change. That is because initially when you are adding dilute HCl, its effect is getting neutralized because of the presence of the base. Only after some time you will see this change in color because after some time this NaOH has been all used up. So there is no more NaOH. And then you see that the color has changed to colorless, which means that the solution here is now acidic in nature. Now, for your better understanding, what you can do is you can again start adding NaOH drop by drop. So now basically before the step 3, now you have this acidic solution, right, which is colorless. Now you start adding NaOH drop by drop. What would you see? So initially again you will not see any change, because initially when you are adding NaOH, it is getting neutralized by the HCl which is there in the test tube. But after some time what happens? The HCl is all used up. So now what you have in the test tube? NaOH, which is a base. And what is the color of phenolphthalein in a base? Pink. So after some time you will see that the colorless thing is changing to pink again, which means that now what you have here in the test tube is a base. That is, now all you have in the test tube is NaOH. So this is a very good experiment to understand how this entire neutralization reaction takes place. And you know, it's not that as soon as you add acid or base, immediately there's change in color. There is not, because initially if there is a base in the test tube already and if you are adding acid, so initially they are neutralizing each other's effect, so you do not see any color change. So if you have not understood this experiment, please recap it, watch it again, please understand this. This is very, very important. So moving ahead with how do acids react with metals. Now this is again something very, very important. So normally what happens is acid reacts with a metal to form a salt, and hydrogen gas is liberated during the process, right? So what we will understand here is how exactly this reaction takes place. Always remember one thing, acids, they are always willing to lose H plus ions. So that's how they are defined. They always have like excess of H plus ions, and therefore they are always ready to lose those H plus ions because they have it in abundance. So at any situation they are ready to give H plus ions, right? So how do you think they would react with metals? Let's look at this. Let us take this example. Let us suppose we have this acid, hydrochloric acid, and it reacts with a metal, say sodium. So what do you think should happen? So how will a salt be formed? Now what will happen is the metal displaces the hydrogen from the acids. So if you look at the acids, they will have these hydrogen. For example, if you talk about HCl, H2SO4, HNO3, you have the hydrogen atom. So the metal will actually displace this hydrogen atom and take its position. So in this case, what will happen? Sodium will kick out H from HCl and will take its position and will form NaCl. And what will happen to this hydrogen? This will be liberated as hydrogen gas. So this is how a salt will be formed. Now the question is, does that mean that if an acid reacts with any metal, so that metal will be able to displace the hydrogen? No, not really. So there is a catch there. So this is the reactivity series of metals, right? So now this series tells us which metal is more reactive than which metal. So looking at this series, you see that potassium is the most reactive. Then comes sodium, then calcium, magnesium, and so on. Now this means that anybody, like, so we will take this analogy. Let's suppose that there are two players. So somebody who is more powerful will be able to displace the other person with his or her power, right? So the powerful wins. So that analogy works here. So if a metal is more reactive than hydrogen, where is hydrogen in this series? This is where hydrogen is placed. So any metal which is more reactive than hydrogen will be able to displace hydrogen and take its position. But any metal which is less reactive than hydrogen will not be able to do that. So here in this case, if you see sodium, where is sodium? It is here. So sodium is more reactive than hydrogen. So anything which is above hydrogen, they are all more reactive than hydrogen. Right? Let's take one more example. Let us suppose if you talk about this reaction, zinc plus H2SO4. So here, where is zinc and where is hydrogen? So zinc is here. So zinc is above hydrogen. So zinc will be able to displace hydrogen. So zinc kicks out hydrogen, takes its position and forms zinc sulfate. But if at all we set up a reaction like this where silver plus H2SO4, what will happen? There will be no reaction because silver will not be able to displace hydrogen and take its position. So that is the simple logic in this case. So you need to know the reactivity series in order to, understand how the reaction will take place. Now let's see how do bases react with metals. Now, bases react with some metals to form salt and hydrogen gas. So the reaction is similar, but the major difference is that, like in case of acids, like most of the acids react with metals to form salt and hydrogen gas, but that's not the case with bases. Only with some metals they react. Some metals like zinc and aluminium, they react. So let's look at this example. Zinc plus NaOH forms Na2ZnO2 plus H2. So here it forms a salt plus hydrogen gas is liberated. Now this is an important point to be noted that bases do not react with all the metals to form salt and water. Now if I ask you, can you guess why? That why is it that with acids, most of the acids react with all the metals to form salt and hydrogen. But why is it not so with bases? Let's understand this. Now, when we talk about acids and metals, now we all know that metals, they have a tendency to lose electrons. Right? All metals, they have a tendency to lose electrons. Correct? Now, if I talk about acids, what is the tendency of acids? Acids have a tendency to lose H plus ion. Right? What about bases? Bases have a tendency to lose electron or to gain H plus ions, right? Now what happens if I am talking about reaction between acids and metals? Then this hydrogen ion accepts this electron and they form H2, that is hydrogen gas. But if I am talking about reaction between metals and bases, both of them have a tendency to lose electrons. So who will gain that electron? Nobody to gain the electron. And as a result, there is no preferred direction for the electrons to go because everybody is willing to lose electrons. Nobody is gaining electron. So the reaction will not be able to take place, and as a result, in most of the cases, the reactions do not take place, and as a result, bases do not react with most of the metals. In fact, zinc and aluminium are few exception metals which react with bases. In fact, zinc and aluminium, these are examples of few metals which react with both acids and bases, and as a result, they are termed as amphoteric. Because I'm pretty sure all of you know the answer to this now. As we all know that metals like copper and brass react with acids to form poisonous metal oxides and hydrogen gas, and therefore it is advised not to store such acidic substances in these metal vessels. React with both acids as well as bases. So how do metal carbonates and hydrogen carbonates or metal bicarbonates react with acids? So metal carbonate or bicarbonate react with acid to form salt plus carbon dioxide plus water. So you would have noticed something very distinctly, that whether the acids react with the bases or they react with metals or they react with metal carbonates or bicarbonates, the product is always a salt, but the byproducts, like the other products, keep changing. For example, somewhere it is water, somewhere it is hydrogen, somewhere it is carbon dioxide, somewhere it is like a mix of carbon dioxide and water. So let's look at few examples. Let's say Na2CO3, that is sodium carbonate, reacts with acid to form salt plus H2O plus CO2. Similarly, in a similar way, it reacts with bicarbonate or hydrogen carbonate, that is Na8CO3, with HCl forms salt, H2O plus CO2. An important point to be noted here is bases do not react with metal carbonates or metal bicarbonates. So only acids react with these carbonates and bicarbonates, and bases do not. Reaction of metallic oxides with acids. Now metal oxide reacts with acid to form salt and water. Let's see how the reaction takes place. Now with this reaction, you can see that the reaction is very similar to the neutralization reaction, which clearly tells us that the metal oxides are basic in nature because bases react with acids to form salt plus water, right? Now let us perform this simple experiment to see how this reaction takes place between metallic oxide and acid. Let us suppose we take a beaker and in that we take copper oxide, which is black in color. Okay, so the black color thing that we have inside the beaker is copper oxide, so oxide of copper. Now what we do, we add dilute HCl. So dilute HCl is added to it, and as a result, what do we see? We see that the solution turns blue in color. So this blue solution is due to the formation of copper chloride, that is CuCl2. So this is a result of this reaction. When this acid reacts with copper oxide, which was black in color, it forms copper chloride, which is blue in color, and H2O is released. So as a result, you see that there you get a solution which has water plus the color of that solution is blue due to the formation of CuCl2. Let us now look at the reaction of a non-metallic oxide with a base. Now, in a way, just the way we saw that a metallic oxide is basic in nature, similarly we will see that a non-metallic oxide is acidic in nature. Why? Because when a non-metallic oxide like carbon dioxide, carbon is a non-metal, so oxide of carbon is a non-metallic oxide. So when this reacts with a base like CaOH2, we get CaCO3, that is calcium carbonate plus water. So here also we see that we get a salt, calcium carbonate, and along with that we get water. In fact, if you remember the famous lime water turns milky experiment, where you have lime water, that is calcium hydroxide, in a test tube, and as you breathe out, so you breathe out carbon dioxide, you see that the lime water turns milky. So that is due to the formation of calcium carbonate, which is milky in color. Right, so this whole reaction tells us that it is exactly like a neutralization reaction, which clearly means that a non-metallic oxide is acidic in nature. So non-metallic oxides are acidic in nature, bases react with them to form salt and water. Oxides, which show acidic as well as basic properties, are called amphoteric oxides. Examples of amphoteric oxides are zinc oxide and aluminium oxide. So what you would see is, if acid reacts with zinc oxide, what happens? Neutralization. That is, you get salt plus H2O. So this shows that zinc oxide here behaves like a base because it reacts with acid to form salt plus water. Whereas if the same zinc oxide reacts with NaOH, what do we see? We see that it forms Na2ZnO2 plus H2O. So here it shows that zinc oxide in this case reacts with a base to form a salt plus water. That means here in this case, zinc oxide behaves like an acid. So zinc oxide and aluminium oxide are two such metal oxides which behave as an acid as well as a base, and such oxides are called amphoteric oxides. Oxides which are neither acidic nor basic in nature are called neutral oxides. One of the best example is carbon monoxide. So after learning so much, it's time to try out a question. So metal compound A reacts with dilute hydrochloric acid to produce effervescence. Okay, so whenever you have such tricky questions, focus on every word because every word gives you some important information. For example, here the moment I talked about effervescence, what does that mean? So whenever something is producing effervescence, that actually means that water is being produced, right? And that's when you have effervescence. The gas evolved extinguishes a burning candle. Which gas can extinguish a burning candle? Carbon dioxide. So this also means that carbon dioxide is also produced. Write a balanced chemical equation for the reaction if one of the compounds formed is calcium chloride. So you also know that one of the product is calcium chloride. So I think we more or less know all the products. So all the products are calcium chloride plus carbon dioxide plus H2O. So these are my products. Right? We do not know which is this metal compound, but we know that it reacts with dilute hydrochloric acid to form this. Now, looking at this reaction, what do you see? You see that the output is a salt plus carbon dioxide plus water. So what happens? Like in what kind of reaction do we have this? So when a metal carbonate or a bicarbonate react with acid, it forms salt, carbon dioxide and water. So that obviously means that this has to be a metal carbonate or a metal bicarbonate. Now the only metal which is involved here is calcium. That means this has to be a carbonate or bicarbonate of calcium. So this has to be either calcium carbonate CaCO3 or calcium bicarbonate, that is CaHCO3. So these are the only two options which will fit in this case. So with that we can write the reaction, and I think by now all of you know how to balance a chemical equation. It's time to talk about dilution. What is dilution? So we spoke about dilute acids, dilute bases, right? So what does dilution means? When we add water to something. Now adding water to an acid or a base is an important process. Do you know why? Because the process of dissolving an acid or a base is a highly exothermic process. That means a lot of heat energy is generated during this process, and therefore it is a very important process and care must be taken, because there is so much of heat generating out of this process that it can even cause burns. So therefore, it is important that we do it in the right way. And what is that right way to do dilution? So even before we talk about that, let us see what happens. I mean, how do we know that the process of dilution is exothermic? So if you take a beaker and if you actually try to dilute an acid or a base, you would actually see that the beaker turns hot, which clearly tells that heat is being generated during the process. Now it is always recommended that the acid should be added to water and not water to the acid, because when you have, let's say, a lot of acid in a beaker, and even if you suddenly add little bit of water, what will happen? It might happen that too much of it gets generated and it catches fire. The glass container may even break, right? So therefore it is recommended that you take water in a beaker, add acid, and that too very slowly, that too with constant stirring. So when we say that we add acid, it has to be added slowly and it has to be added with constant stirring. So what happens with stirring? So when you are adding acid and you're stirring it continuously, it's like you're mixing it uniformly in that entire solution. But if you suddenly add it, so it might happen that the concentration of the acid immediately becomes very high in that particular locality, and it might generate too much of heat. So constant stirring is important, and adding the acid slowly to water is also important, and you should never add water to the acid. And this is the reason this process of dilution is worth discussing. Quick question time again. Why do HCl, HNO3, etc. show acidic characters in aqueous solutions, while solutions of compounds like alcohol and glucose do not show acidic character? So now I have to ask you a question. So here on the screen you see the structures of all of these. This is HCl and HNO3, and this is alcohol and glucose. Now a quick question. What is that primary thing that we look for in an acidic character? So in acidic character, the first thing that we look for is H plus ions. Excess of H plus ions, it is an acid, right? Now if you look at structures like HCl and HNO3, you clearly see that they have hydrogen, which they can very easily release when in water. So they readily release hydrogen ions in water, and therefore they are acidic in nature. But when you look at the structures of glucose or alcohol, you see that they also have hydrogen, but they do not release hydrogen ion in water. That is because the hydrogen in their case, they are very strongly bonded either to the oxygen or to the carbon, but they are like strongly bonded, and therefore they do not readily come out of it come out of the structure so easily, and therefore they do not show acidic character. I hope with this video you got a fair idea on how do acids and bases react with metals, their oxides, their carbonates, their bicarbonates, and so on. So do share your feedback with us, and also let us know in the comment section if this video helped you. So in the next video, we are going to talk about the strength of acids and bases.